Okay, thank you very much. Okay, I'd like to thank by thanking the organizer for inviting me here. I'm very happy to be able to present this recent work. This is not exactly in the core thing that I usually do at the Max Planck Institute, but since it's fit very well within the scope of this workshop, I thought I would talk about those results. And I hope you will forgive me if some parts sound a little amateurish compared to the excellent talks we had about other approaches to parameter estimations before. Okay. So let me start by explaining that I think in general there are sort of two ways to estimate things. There is a dumb way, and it's not here a negative thing actually. You compute the theory predictions, and then you fit these predictions on simple observables that you are able to compute. And there is a smart way, which is that you really reconstruct the optimal estimation of the thing you do not know from the whole data set. And the objective of this talk is to discuss these approaches in the context of continuous measurement and how they allow to estimate parameters in different ways. And the small novelty in this talk, I mean, most things would be recalling things that are actually, I think, well known in the literature. But the small novelty is that there is a closed form formula for endpoint correlation functions in continuous measurement that makes the dumb approach more systematic than that one might think. Okay, and this will be like the what the new thing. Okay, so and for that matter, I know Andrew Jordan talked about continuous measurement, but I will reintroduce them. I will present the smart parameter estimation method in this context, then present the dumb parameter estimation, compute the correlation function that it requires, include imperfection, and then discuss a bit what are the drawbacks and the interest of the two approaches. Okay, so let's start by continuous measurement. To obtain a continuous measurement is actually, I mean, the big picture is actually quite simple. You start with a quantum system, and you just send probes to this system, and they interact, they get entangled, so they sort of catch information about the system, and then you projectively measure those probes. So it's like moving the Heisenberg cut of where you apply the projection postulate from the system to one step further. And given those measurement results you get on the probe, you can sort of reconstruct the trajectory of the system you measure. And if you want to be a little pedantic, you call that you can even call that a discrete quantum trajectory. It's a sequence of states that are random, and this randomness just corresponds to the randomness of the measurement result. So this is sort of to show the Hilbert space, and you have your density matrix or your state like doing a random trajectory in this Hilbert space, a jumpy trajectory. And then you understand, you have the feeling that in the same way random walks have a limit that is a Brownian motion, you can take the limit, a certain scaling limit of this process where the system-probe interaction becomes infinitely weak and the probes are sent infinitely fast. Okay? Of course, you need to make this interaction weaker and weaker, otherwise the Zeno effect will freeze everything and nothing will happen anymore. But it turns out there is a non-trivial scaling limit in which you get the equivalent of a Brownian motion in Hilbert space. And then a continuous quantum trajectory is just just a state or density matrix evolving continuously in time, and the associated measurement signal, which in the discrete case is just, for example, plus or minus 1, and in the continuous case becomes a Gaussian random variable. And this is essentially a central limit theorem result. So it doesn't depend on the sort of probe you start with. I mean, you can start with probes that are harmonic oscillators or qubits or whatever, and if you take the proper scaling limit, you will always get a continuous measurement of that kind. And so if you do that carefully, you obtain first, this continuous measurement, you can obtain them in a proper limit of discrete situation, such as the one that of the LKB experiment with Rydberg atoms. So showing again the most looted pictures in this old workshop. So where you send, this is exactly the setup, the abstract setup I mentioned. You send Rydberg atoms through a cavity, they get entangled, you measure the Rydberg atom and you reconstruct the state in the cavity. But you can also get a sort of situation that are even closer to the continuum limit with homodyne detection or other setups like quantum point contact for quantum dots. So this follows a bit what Andrew Jordan presented on the very first day. And now for the formalism of how does the state evolve when it's subjected to continuous measurement, the density matrix now obeys a stochastic master equation where you have the first term is the evolution in absence of any measurement. The second term is the dissipation, the decoherence added by the measurement. It is what you would get if you were to discard all the measurements. And the last term is the innovation that comes from the fact that you condition on the measurement. So this is a nonlinear part that makes the continuous measurement progressively collapse in the pointer states. And the signal also depend on it is basically contains the deterministic part, which is the average value of the observable you measure plus some white noise. And these equations were derived quite a while ago with many different techniques by many different people and with many different intuitions in mind. So sometimes to phenomenologically describe a certain limit of discrete interactions, but also sometimes as proposals to say of new foundations for new foundations of quantum mechanics. So say where people were saying, okay, why not take this as the new Schrödinger equation of quantum mechanics with appropriate observables? So this continuous measurement have been used in an extremely wide variety of contexts, but now I will focus on the application in experiments, not in their foundational aspects. And from now on, I will sort of forget how they are implemented in practice and just consider that this is the sort of evolution we are given. This is not perhaps to make it a little clearer. It may be helpful to explain what such an evolution gives in the simplest non-trivial case. So you consider a qubit that is continuously monitored with the previously mentioned scheme, and you continuously measure sigma z, and you even discard the Hamiltonian evolution could have or any other thing. You just consider the pure measurement of this qubit. You start from the stochastic master equation I wrote before in the most general case, and you instantiate it in this example. And what you get is that the probability and the phase obey the equation that I show here. So let me start just by the phase in the sigma z basis is decreasing exponentially fast. But I will focus more on the probability. The probability has an extremely simple and a stochastic differential equation. It's basically just pure noise with a diffusion coefficient that is the probability times 1 minus the probability. So the probability is going to move, and the noise, it will stop moving when the noise vanishes. And the noise vanishes when you reach perfect certainty. So when you reach p equal 1 or p equals 0, okay? So it's quite intuitive what is going to happen in both cases. And so if we look at the probability, for example, let's say I start with a probability 0.3 to be, I don't know okay, to be, say, in the plus state. And then after a while, it evolves randomly and converges to here 0. And this is, if you want, we have just expanded the discrete projective measurement into something that takes time. Okay? But of course, this is random. So if I were to start many times for this point, from this point 3, I would converge to 1 or 0. And of course, the probabilities to end up here is 0.7, and the probability to end up here is 0.3. So it's exactly what the bound rule would predict. Okay, so we have, I mean, this has to be consistent. Otherwise, continuous measurement would be sort of useless in that case. And in this qubit case, in this pure qubit case, is one of the few cases where you can actually compute the distribution exactly. So if you start from a Dirac, so at 0, you see that the distribution spreads out and for a larger time becomes very bimodal, and in the end, like 2 Dirac points in 0 or 1. Okay, so this is to give a sort of intuition of what happens with a continuous measurement. Then a question I've been very interested in for a while, and which I will not talk about today, is how then what happens when you start putting Hamiltonian evolution and have a competition between this continuous measurement and the Hamiltonian evolution and what you can say. But now I'm going to focus on how continuous measurement can help with parameter estimation. So in a way, attacking the same problem Andrew Jordan was considering on the first day, but from a slightly different angle. And this is the question I will now ask, is that I assume that I have a continuous measurement evolution, but some parameters in the evolution are unknown. And for example, I take here the Hamiltonian. I consider some parameters in the Hamiltonian are unknown, but you could imagine that, say, the measurement strength gamma is unknown, or that the measurement operator itself to measure is unknown. Like many things could be unknown. And the question is, how do you estimate this parameter from the continuous measurement record that you have? And the idea is to turn, back parameter estimation into a filtering problem. Basically, you just imagine that the hidden parameter, the parameter you don't know, is just an internal degree of freedom of your system, and that you have a sort of incoherent superpositions of this hidden parameter. And because of the continuous measurement, you will try to collapse on one of the values. So in practice, how it is, like you extend your Hilbert space with an auxiliary Hilbert space that contains a bunch of possible values of your hidden parameters as pointer states. And you extend your density matrix, the Hamiltonian, and the operator you measure in the most natural way, okay? Just take it diagonal in this basis. And then you solve the stochastic master equation on this extended space, okay? And basically diagonality is preserved. The density matrix will stay block diagonal in this enlarged Hilbert space, and the probability, basically the trace of the block will converge to, all the mass will end up in one block, which will give you the value of the parameter you are trying to measure. So it's like, in the same way, in the trivial case, you are collapsing a state into one value or the other. Here, in the same way, you are collapsing the hidden parameter into one value or into one value out of a bunch of values. So, of course, you can prove that this works in a rigorous way, and this is really, I mean, totally, this is something you can do very well, but let me just give the intuition for why it works. So, why does it collapse? I mean, this is really the intuition that you have for continuous measurement, that this is going to collapse. In a way, we are just doing a superposition in parameter space instead of physical space, of state space. So this is the intuition for why it collapsed to something. It doesn't really tell you that it will collapse to the correct value. And for that, I think the good intuition is to see that so long as you are considering only diagonal matrices, continuous measurement is exactly equivalent to standard stochastic filtering. Okay? So you can imagine that there are hidden variables that are really there and that your continuous measurement is just revealing them. So basically we are just doing, if you have only diagonal density matrices and everything is diagonal, continuous measurement is only hidden Markov models where you reveal the hidden values. So in that case, because we are diagonal in this parameter space, in this space of hidden parameters or unknown parameters, we are just revealing the predetermined value. And once you understand this in terms of hidden variable and hidden Markov model, this is very easy to, you could easily extend to a fluctuating unknown parameter that is doing a Markov chain and fitting even the parameters of this Markov chain. So I think this is all very nice. Of course, there is a little first subtlety in this context, which is that you see at the beginning I assume that the parameter that is hidden can take only a bunch of values. And you really have to discretize your Hilbert space, your auxiliary Hilbert space, and it needs to be very large if you, if you want to have a high accuracy. But of course, you can be a little smarter and do some resampling. So first, assume it can take a bunch of values very spaced out. You find this will collapse into one value. And then you refine. You now consider that the parameter it can take many values, but only in this range. You run your algorithm again. It will now collapse to this value, which is more precise, and you do it again. And at some point, you will have such a level of precision that the collapse takes too much time or just never happens, and you will have them reach the maximum accuracy that you can get. And there is this very nice paper with Benjamin Huard and Pierre Rouchon and colleagues that shows the estimation that applies that to something quite a bit more subtle than what I showed, so not a hidden Hamiltonian, but the efficiency of the measurement itself. And they start with, you see, efficiency 0.1 or 0.26 or 0.4, so very spaced out values. And they run the stochastic master equation, and it basically collapses in the efficiency space quite quickly. It tells them it's 0.26. And then they refine around this value. And then they refine again around this value up to the point where it doesn't really collapse to a definite alternative between the two. This will be for me, like the example of sort of the smartest possible way you can estimate parameters in this context. That's clearly the best you can get with the data you have. Okay, this is the Bayesian optimal. But there is, I mean, and I'm not. Of course, this works, and this is actually done with real data. So I'm not saying it cannot be implemented. Of course, it is efficiently implemented. But there are some practical difficulties if you want to do that. So the first practical difficulty is that you have to reconstruct the state. And the state is a complicated nonlinear function of the measured signal. Basically, you have to solve a nonlinear stochastic master equation to reconstruct the state. And further, the signal you have that I showed in the sort of abstract formulation of continuous measurement is not the signal you get in practice. So if you look at, so this is, again, this is taken from the setup of Benjamin Huard's group. If you have your quantum system, I mean, then there is a whole detection chain with amplifiers that will filter your signal and basically smooth it out so that you will lose some of its features. So you have to also take that into account. Of course, this can be done. You have to discretize. Okay, maybe discretize is not like to sample your signals at a very high frequency. You try to deconvolute the filter of the detection chain as well as you can, and then you numerically integrate the stochastic master equation to reconstruct the trajectories here. And this can be done, although it requires pretty good electronics and pretty smart integration schemes. But in the future, if we want to do that for more complicated quantum systems, I mean, at some point we will hit the fact that it becomes hard to, this requires reconstructing states, so we will have a problem if the states become big. In the end, if our schemes require effectively solving what the quantum system is doing, this is going to defeat the very purpose of quantum technologies, okay? That the objective will be to process this quantum information with the quantum system, not have a classical simulation, not require a classical simulation to do it in parallel. And this brings us to the other option. So smart parameter estimation that I showed is clearly mathematically optimal, but sometimes it may be overkill. Maybe we don't require that much precision or hard to implement. If the Hilbert space is very big, or if you require a very fine sampling of your signal. So smart parameter estimation, you reconstruct a non-trivial function of the signal, here's the state, to obtain directly the probability of the unknown parameter. Dumb parameter estimation, and again, I don't say that in a negative way, is you compute a trivial function of the signal, something that you can obtain very easily from the signal, and then you use the theory to relate it to system parameters, and then you just fit the theory on the data you have. This is clearly suboptimal in general, but what you might hope is that it is good enough in practice. And a good candidate for dumb parameter estimation, so for the easy function of the signal, is just the endpoint correlation functions. Okay, they are readily available. What is the advantage? I mean, it only requires analog manipulation of the signal. Okay, you can compute the endpoint correlation functions just with delay lines and multipliers. So in principle, you can do everything analogically without ever acquiring a very refined discretized signal. And you can include all the imperfection in the theoretical fit. So you can include the fact that your signal is filtered, you can include imperfection in the measurement and so on, include them in the theoretical fit, and you don't have to deconvolute these imperfections that you have. So that's the idea. But this requires basically, if I want to fit, I need to know what the theoretical prediction is for that. And it seems, then you run into the issue that you have to compute this endpoint correlation function in basically the most general context you can think of. And the issue is that although you can sort of derive it, by following all derivations, you can extend all results to get a formula like that, but it seems to me that either it is not known or insufficiently known that in the general continuous measurement context you can compute those functions exactly in the most general case. So the setup I consider is you have some very generic continuous measurement. You have a system evolving with a Lindbladian that is given, plus the continuous measurement of n operators, and you have the n signal associated to this measurement. So this is a fairly general setup, and that could be generalized to something even more complicated. And then the objective is to compute this endpoint correlation function of the signal as the function of the system dynamics. Okay, if you can do that, then you can fit things. So yeah, okay, as the function of the system dynamics, as the function of the operators you measure and the efficiencies, and I could add even as a function of the imperfections of your system. And actually, there are many ways to derive them. You can use a quantum noise or equivalently a continuous matrix product states. I will come back to this approach later. Or you can work with a discretized version, conjecture what the formula looks like, and take the continuum limit. So I took an alternative way, which is sort of more pedestrian, but has the advantage of using only basically the Ito formula and completely standard formula in stochastic calculus, so it's sort of rigorous and clear, although maybe slightly less intuitive than the other proofs. And let me not bore you with the derivation, which actually is trivial, although a little bit pedestrian in the general case. But the idea is to introduce a generating functional, okay, exactly like you will do in quantum field theory for the correlation function. And then you realize that this you can write a sort of auxiliary density matrix such that this generating function can be written as a trace of this auxiliary density matrix. And then you just solve the equation for this auxiliary density matrix. And as the last step, you carry the functional derivation differentiation of this generating functional that provides you the correlation function. So this, at every step, you can just use standard stochastic calculus techniques. And in a way, I'm not sure there is anything so interesting in the proof. So let me just stop at this sketch, and if you are interested, I mean, you can check the reference I'll show at the end. And the important thing is, what does the result look like? So at the very end, if you look at the correlation function, the correlation functions will contain a lot of equal point contribution coming from the fact that you have white noise. But let's forget about this contribution for now. So let's consider a correlation function for times without equal time. And in that case, you see it takes the form of a trace of the initial state time a CPTP map, then the insertion of a superoperator, then CPTP map, and then, and so on. Where the CPTP map here is just the evolution, the evolution average over the measurements. So if you discard all the measurements, and graphically it takes this form, like you have the initial state, a propagator, okay, given by this evolution in absence of measurement, then you insert an operator, propagator, insert an operator, and so on. So this is very easy to compute in practice, okay, and this is for most systems. I mean, you can even write exact expressions for the correlation function, like closed expressions. And of course, yeah, and this is not so trivial to sort of find the genealogy of this formula, because they are in many places it is there, although not entirely explicit, or it is the exact same form but to compute something different. But yeah, so it's I'm not so sure what is the paternity of this formula, but I mean it doesn't really matter for what is going to follow. But yeah, the important thing is that it can be solved exactly in terms of the function of the system parameters. So in practice, I mean, the world is a bit more complicated than that. So the signals you have, they are filtered. So basically, instead of being the signal at time t, you have a sort of window that smears the signal you actually measure. And so the corresponding correlation functions actually, they are not so much acting on n times, but on n windows around those times. And because of that, even if you look at correlation functions that at different times, you will pick up the delta contributions because of the fact that the filtering of the amplification chain spreads your signal in time. And of course, if the bandwidth of your amplifiers is very, very large, this effect will be minimal. But if the bandwidth of your amplifiers is not so far from the timescales you're probing, I mean, this correction will be very big to the point that it will dominate everything. So it's important, but in our case, it's not so much of a problem because we can just include the effect of such filtering into the prediction and fit it with everything else. So you fit all these imperfections as new unknown parameters as well. And this can be included, and this is a little more cumbersome because you have in this context an equivalent of Wick's theorem to compute all the equal time contribution, and you have to keep track of all the possible contributions. But I mean, then you get a formula of this kind plus all the possible contractions that capture the equal point contribution. But the only thing that really matters is that it can be done. And to illustrate that, let me show a quite, in a sense, the simplest non-trivial example I could think of, and it's actually inspired by a very recent preprint by Benjamin Huard's group that I've shown before. You take a qubit without proper dynamics, and you continuously measure two non-commuting operators. Okay, that's sort of, so it's sufficient to make the dynamics non-trivial. And you just run the previous formula, and you get that the two-point function for the correlation between the signal associated to one detector and the signal associated to the other detector takes this form. I mean, it's okay, like it's just somehow to show that in general you can run the previous very general formula and instantiate it as a function of the system parameters. And what you can see in this case that clearly from this formula you can identify all parameters. Okay, if you give me the function, it is enough to recover the values of all the hidden parameters. Okay, this is a simple case, so in that case this two-point function is enough. Of course, this one doesn't depend on the efficiencies. You see, it is totally independent of the efficiencies because it doesn't capture equal point contribution because I take different detectors. But I could also take the equal point one to get something that depends on the efficiencies. Of course, you can further, this is without any imperfection of the detection chain, but you can add a low-pass filter with a certain bandwidth lambda, and this will smear the regular part of the correlation function, but also picks the otherwise hidden equal point singularities. And what you get for the correlation function is then something like that. So here, this is the setup here, where I take values for gamma x and gamma minus. So the time scale of the measurement is of order 1. Okay, this is what sets the time scale in my problem. And then I take lambda to be 10. So if you want, like the bandwidth of the amplifier is 10 times the time scale of the problem I consider. And if I look at the correlation function, so this is the correlation function that I've shown before. The black line is the exact if there were no imperfection in the amplification chain. And the dotted line is taking into account the fact that there is a filter. And this is in orange is a numerical simulation with very few trajectories. I mean 10 to the 4 in length and simulated in the stationary state. And you see, okay, I mean, naturally it fits a theoretical prediction. And here I show also the XX correlation function. And this one has a Dirac distribution in the center. And so you see, because of the amplifier, you pick a huge correction from this Dirac for a short time, naturally. But again, this is not a problem because you fit it as well you fit it as well and you include it in the estimate. So you don't even try to deconvolute it. And you can even, so this is sort of nice because you don't have to go to very long time where estimation of correlation functions become inefficient. So you can still estimate at very short time inside the bandwidths of your amplifiers and still get decent fits. Okay, so let me sort of change entirely now for this last slide and mention briefly that what I did is in a simple example, it could very well be that it works only in that case, and that in general, I mean, there is a question of, in that case, you can read all the parameters in this two-point function, but it could be that for more complicated quantum systems, you have to go to the thousandth point correlation function to know all parameters. And for that matter, but to explore this problem, actually, I had nothing new to do. Because you can realize that continuous matrix product states, so maybe it's familiar to a small fraction of people here, they are a variational class of states for 1+1D quantum field theories. But it turns out the formalism is completely equivalent to continuous measurement if you use the dictionary that the quantum noise is the quantum field, and that the small system of interest for us in continuous measurement is their variational parameters in that case. So they sort of simulate quantum field theories as the quantum noise of something interacting with a small system and use this small system to parameterize the quantum field. It doesn't really matter, but the thing is, okay, this is used, especially at the Institut where I am now in Garching, where this is some sort of active area. And it turns out there is a result, but by Izard's group from 2013, where they show that the endpoint functions of a CMPS in the thermodynamic limit can be generically reconstructed from their 2- and 3-point functions. So what does it mean with the translation, with the dictionary in our case? It means that all the parameters that can in principle be estimated in the stationary state can generically be estimated using only 2- and 3-point correlation functions. Of course, there is a strong thing that you need, of course, that they can be in principle estimated, because if you have parameters that have zero impact on the statistics of the signal you measure, of course, you have no way to measure it. But if it has an impact on the statistics and it's generic, of course, systems in practice may not be generic, so you have to go further. Usually the 2- and 3-point functions are enough. So, I mean, there is good hope that this technique is of using basic correlation function generalizes to more complicated setup. So let me now leave you with this summary. So there are smart and dumb ways to estimate parameters. So smart is optimal, but difficult and possibly one day intractable. Dumb is suboptimal, but easier to implement. So here, the dumb method I show relies on the computation of signal endpoint function, and we are lucky because, I mean, for general non-Gaussian theories, it's complicated to compute endpoint functions, but for the signal coming from continuous measurements, it's one of the few cases where you can compute endpoint functions exactly, and you can do that in full generality, and you can include detector imperfections. And more generally, I think this is something we should think about, because studying and controlling quantum systems without ever reconstructing their state and focusing on simple functions is easier, and in the future it's going to be the only way we'll have to do things. So being dumb is probably the future, like once we have big quantum systems. And if you are interested in what I just presented, you should check this recent paper I put on the archive. And for that, I thank you for your attention.